All right, good morning. My name is Patrick DeSantis. This is my first time at DEF CON. My first time speaking at DEF CON, so it's pretty awesome. Thank you all for coming out. I'm going to talk about finding backdoors on embedded devices using pretty common, not very sophisticated techniques. So the talk is from box to backdoor. So I work at Talos, and over at Talos we built a automated kegerator using industrial control systems components. On the screen there you've got on the left a Allen Bradley programmable logic controller, and on the right is a Moxa wireless access point. So they had the very critical function of pouring beer for us. So we've got automated beer pouring, and the whole point of putting this together was, of course, so that we could hack it. Because we were going to hack it, we figured we got to take a look at the devices in there and see if we can knock off any low-hanging fruit. So this is kind of a story, narrative of just one person's thought process walking through, beating the shit out of two very expensive low-end embedded devices. So the first one we'll take a look at is the Moxa. It's a wireless access point. The too long didn't read is it's just an 802.11 wireless access point in about $1,000 enclosure, but it's really like a $40 router that you would have at home. It's in-rail mountable. It's marketed as being used for your automated guided vehicles and automated storage and retrieval systems. So these are creating mesh networks on vehicles in like warehouses. Doing a little Google, you'll find out that they're also used on trains, which is kind of scary. Ours, of course, is there to pour beer. And also it's unbreakable, which we all know. Sure. And it took about 5 minutes to know that was right. So, hitting this thing, you start out with scanning and doing your enumeration and walking through and everything, but the device itself was so limited that it actually made testing more difficult because every time you scan it, it's a DOS. It constantly crashes. Constantly. Like you want to fuzz. Literally sending get A causes a seg fault in the web server. So it's like, how the hell do you fuzz that? You can't send anything that if it doesn't start with a slash, seg fault. And from the outside doing black box testing, I don't know this is seg faulting. I just know that the web server stopped working. So I got to reboot the device. There's also no OS access. We have this very limited shell. Almost all of the configuration is done through the web application, so this isn't even a very functional shell. So take a look at the firmware. Hit it with binwalk, got no results. Look at strings, not very promising for strings. So do some entropy analysis, binwalk feature in binwalk to look at the entropy of the actual binary file. Looks like it's probably encrypted. So we're not going to get anywhere looking at the firmware. We got to, even though the device is limited and it constantly crashes, we got to go back and hit the device. And these are the services that we have available to us. So we have SSH and Telnet. Both of those are going to drop us into that limited shell. We have web, and then there's a Moxa protocol that's used for configuration, and that's a whole can of worms that could be about 2 or 3 talks by itself. So I'm not even going to go into that. We're just going to look at the other stuff. So taking the web app is probably the lowest hanging fruit on there. Right from the very first thing I see at the login page is the username is read only. You can't edit the username, which doesn't make a lot of sense. So at that point, is there even a user? If there's only one user, there's effectively 0 users. And the password field had a very short max length. I think it might have been 12 characters. I'm like, okay, this is not going to go very well for this device. But then looking at what it actually sent. So this is the post. the whole session is based on the value in the cookie. The post data, you can put anything you want in there. It does not matter. Password's not being sent in the clear, which is good because there's no password being sent. But the only thing it's using for authentication is the session token in the cookie. Later on, after we pull the binaries off the device, throw it in IDA, we'll find out that admin user is hard-coded. It is the only user, and it's right there in the binary, so you can't even change that. So you've got, your username, password. Well, there's only one username, so all you have to do is know the password. As part of authentication, the web server itself passes you a nonce, a number used once, supposed to be used once. In this screen, we see that we're passing the time to try and add some randomness. Actually, that doesn't mean anything. You can put whatever you want in time, and you're going to get the same nonce back. So I don't even know why it's passing that. It's completely irrelevant. And in fact, it's not a number used once. It's a number used over and over and over and over. It's a quick script to generate cookies based off of, it's just password, concatenate the nonce, MD5 hash, that's the session value. And if we hit the web server with any type of request, at least once every 5 minutes, our nonce will never change. So the first, 7 or so up there are all the same. It's every minute, and then I skipped it to 10 minutes, and you can see the last 3 are actually different nonces. So if you're running this script, then the nonce will never change. We only have one user, and it's not using the password for authentication, so essentially there's only one valid session token at a time, and it will never change as long as the device doesn't go to idle. So can we steal that session token? Probably. I probably wouldn't be here if we couldn't. So we start out with everybody's favorite lame web app vulnerability, cross-site scripting. There were a lot of cross-site scripting vulnerabilities in this web application, but what good is cross-site scripting if you only have reflected cross-site scripting? I hear a lot of people say things like, oh, that's great, you can hack yourself. But there should be a lot more respect for reflected cross-site scripting when it's used in web applications that do not lock down that session token. In this case, we can embed this in something like an iframe or an HTML and an email. If it's viewed by somebody who has a valid session, or who has a cookie with a valid session token, then it actually passes back that session token to us. So we've got a netcat listener, somebody opens up an email or a web page, whatever, with our cross-site scripting code, and we get that valid session token. It's just all we need to authenticate. So we have the username, it's hard-coded, the nonce, we froze it, we stole the cookie. We can crack the password now, but we don't need to, because the nonce isn't changing. So our session token will never become invalid unless the device goes idle or gets reset. So we're logged in, we have that session token. Once anybody who's ever done any web app testing before, if you've looked at networking devices, you probably start drooling when you see this, but actually doing some kind of injection in the ping form on a web app, that hasn't worked in 15 years, right? When was the last time you just put something in there without any kind of obfuscation and got a result? Serious. That was horrible. So we don't have legitimate OS access, but as a busy box, we have command injection. We can bind telnet to a port and have BusyBox pass the shell out to your. So we have root shell through OS command injection. So no longer limited to that basic command line interface, no longer limited by the web app, full root there. Another way that we could have gotten access, cross-site request forgery. This form does the same thing as this. and it will auto-submit. So kind of similar to the cross-site scripting, if an admin or somebody who has logged in has a valid session in their browser, or valid session token in the browser's cookies, views a page with this code, this HTML, if JavaScript's enabled, it'll auto-submit and open up Backdoor for us. Netstat on the top before, Netstat on the bottom after. We can see that it is listening on port 9999, so all we have to do is connect to it. So we've got from the very beginning, freezing the nonce, to have a permanent session or a never expiring session, and then 2 different ways to get our command injection, either through cross-site request forgery or cross-site scripting. And then that gives us our root shell. So we're on the box, smash and grab, steal everything. These are all MIPS binaries, which makes it a little tougher to work with, but you can drop them in IDA and have all sorts of fun with them. Anybody out there wants to go to town on these? I only spent 2 weeks total looking at this, so there's a lot of stuff still there that I never hit. Get with me after, we can talk about it and get a lot of CVEs out of this if you want to poke at them. So the talk is about backdoors. Where is the backdoor? We have command injection, we have root access, but there is an actual backdoor account on here. If you take a look at the accounts that are listed, I went through all these and found that there is only one that is not either disabled or has an invalid shell listed, and it's this 94J whatever user. That password hash, you can decrypt it, and it's just Moxa IW, and that doesn't work. So using the access we have on the device, doing things like grepping memory, because everything in Linux is a file, you can grep through memory. You find the Moxa IW string with the %s, so the format string, and it's around commands like change password or create user. Thinking that maybe this was like really easy, try Moxa IW %s as the password, does not work, which didn't think it would, but I wouldn't really be surprised if it did. So looking at the binaries that we grabbed when it said smash and grab all the binaries, dropped a couple in IDA. This one, to make it easy to see, we know the root password, or we know the admin password is root because that's the default password. So it's setting the admin password to root, and then it is setting this backdoor account password to Moxa IW and whatever value is being held in var 120, which is root because it never changed after the admin password was set. So the backdoor password is Moxa IW root. It's hard-coded, it's an initialization binary, and it runs every time you turn the device on. So even if you delete that user, once the device is rebooted, the user is back. So now we have root shell with an account. We don't have to exploit it anymore. Full operating system, backdoor access to the device. What do we do with it? We already have root. What else is there? There's a lot of binaries on this system. We can mess around with it. You got things that you can do with like IP tables and tunnels and steal traffic, and you can put kernel modules in there if you want. But I really just want to brick the thing. That's all I'm interested in. So very easy soft brick. We have root, kill all 5. It kills all the processes except the one from which you ran kill all 5. And you can do things like mount and unmount various volumes in the file system. They're all read-only except for one, so once the device reboots, it's right back to normal. Soft bricks are fun, but they're not as fun as like firm bricks or hard bricks. So I don't know how I did this. I was trying to brick it, and I bricked it, but I didn't expect it to brick when I did what I did. So there's a set, I don't know what this firmware set environment is binary is supposed to do. I was fucking around with it. I was passing different options to it, and then I did a mount remount and I rebooted, and that was the last time I ever saw that device. Yeah. So that one's done. I only have 2 of those, and I didn't want to brick the other one because it's actually pouring the beer. So I probably will never know what really happened, but we got 13 CVs on that, and like I said, we spent 2 weeks total on it. Most of the time was trying to figure out what was wrong. Didn't even look at the wireless stuff, and that's the whole point of the device. Also, when the patch came out for the device, we went through the whole responsible disclosure process. Patch comes out, apply the patch. First thing I do is try to log in with the backdoor, and it logs me right in. I said, what the? They didn't even patch the one thing, like the most important thing. And then looking at they have their SVN notes in here, and it actually calls out Cisco Talos in their SVN notes, but they didn't patch the vulnerability that we disclosed. So we waited a couple weeks, and they put out another patch, and they actually fixed the backdoor. So the backdoor's not there anymore. Well, it may be. It's not there in the way that you can't just log in the way, I'm pretty sure it's probably still there, and you could probably enable it, but I tried to log in and it didn't let me. I said, okay, that's all I want to know. I don't want to know anymore. I'm moving on to something else. So let's hit the PLC, programmable logic controller. These, if you're not familiar with PLCs, they're computers that are the boundary between the physical world and your TCP/IP network generally. That's oversimplification, and that's wrong on like 5 different levels, but for what we're doing, that's how it works. They have inputs and they have outputs, and those inputs and outputs, they come from sensors and they go to actuators. So this is what's controlling the actuators on our kegerator that's opening and closing the tap. So we chose the Micrologix 1400 because it has inputs and outputs already in it. You don't have to buy extra modules. So it's popular generally because it's affordable and it has everything built in. It's got Ethernet, so you can put it right on your network. You don't need to buy a separate Ethernet module, and it has I/O. This is what Micrologix, Allen Bradley, Rockwell, this is what they advertise its use. It's not used in like big SCADA systems, but smaller SCADA systems, micro SCADA systems they call it. We're going to hit the firmware just like the last one, but there isn't really much going on that we can see. There's strings. Can't really get a lot out of them. You can see there is some actual text in there, but it's probably compressed. And hitting it with binwalk, you can see the addresses. It jumps essentially right to about, was it 160,000? Hex 160,000, and it's all web files. And all the HTML files and JavaScript and everything are there. They're not encrypted, they're not compressed, they're just plain text. But there's a whole section of the firmware that binwalk didn't give any results for. The first 160,000 hex bytes there. So if we look for opcodes, it's going to tell us it's cold fire processor, which opening it up and take a look, it is actually a cold fire processor, so that's good to know. And here's our entropy analysis for the firmware file. So I think the first half, or the first third of it or so is compressed code, and then there seems to be some data structures, some tables, and then the last part of it is just raw HTML, JavaScript, CSS. I point out SNMP separate here first, and anybody who does pen testing or security assessments, like, do not forget about UDP. I cannot count the number of times SNMP has given me more than I could have hoped for. And it turns out this is one of those times. So you've got your basic OID, your basic MIB, when you run SNMP enumeration tool, that's going to go through kind of the defaults. A lot of people stop there. Don't stop there. Find the vendor's MIB, find their OIDs. Each vendor has one or more. In this case, this ISO 3614195-130, that is one of Allen Bradley's. So you can find it here using just the public community string, or you can do a Google search and look for Allen Bradley MIB, and you'll find that you can just get it off the internet as well. So if you do this SNMP walk on that MIB instead of on the defaults, so you add the 136.14195, it'll start walking those OIDs. And something stands out to me on the bottom of this. I see public and private, which are default SNMP community strings. But there is another word there, and it's wheel. What the hell is wheel? I don't know. Well, let's try it. Let's see what it does. I can read with it. So SNMP walk, community, wheel, version, and then the IP address. So example of using the private community string to set a value to hacker, and then using wheel to set it to Uber hacker. So wheel is a privileged, undocumented SNMP community string. So even if you're looking to lock down the device, you want to change the defaults, there's one there that you don't know about. It makes it hard to change something that if you don't know it's there. And nobody's scanning their devices. They're running SNMP walk on their own devices. So this is an example of a firmware update. SNMP is used to update the firmware on these devices. So SNMP sets a value for the path, the TFTP path, where the file is, the firmware file. It sets IP address for the TFTP server, and then another value, essentially you change it from 1 to 2, which initiates the TFTP transfer. So if you can talk to the device and SNMP is enabled, you can modify the firmware by first giving it your IP. You have to set up a TFTP server, put the firmware on, give it your IP, give it the file name, hit send it to, and it will start flashing. So it reaches out, it grabs the firmware, it checks it to make sure that it's valid, or it has its integrity check, and if it passes that, then it actually flashes the firmware to the device. So how's it checking to make sure that that firmware is actually valid? It's only using checksums. Checksums are very easy to get around. They're not used, or they shouldn't be used, in place of things like signing. They should only be used to validate that what I sent to you is what you received. Not that what I sent to you is not malicious or is what I created. There are a lot of ways around checksums. There are a couple very easy ways. Just swap some bytes. As long as the end result is zero sum. So 1, 2, 3, 4 is the same as 3, 4, 1, 2, or 4, 2, 4, 2 is the same as 4, 1, 4, 3. You go down 1 and up 1. As long as the math works out the same, it doesn't matter what the bytes are. So something as simple as this changing 6E, 6F to 6F, 6E, just essentially swapping ASCII NO to ON for one of the files on the web server, and then visiting ON TIFY instead of NO. It actually tries to pull that page. That page doesn't exist, so once you authenticate, you get a server error, but it shows that we just modified firmware and flash the device with our own modified firmware. Very basic example of it, but it's the first step in a better proof of concept. So take it to the next step. Instead of just flipping some bytes, let's actually change some, we'll stop right, we won't change code yet, we'll change some text. So here, changed the word remote to hacked, and then made the compensating changes. You can see from 4.4 to 7.0 to make the math work out right for the checksum. And then flash the device and reboot, and it comes up with our new firmware. So we are modifying the firmware on this. The screen I showed you that showed the breakdown of the firmware, the first part of it is compressed. We can go in there and change the instructions. They're cold fire instructions. The device will take our modified cold fire instructions. It will take that firmware, it will flash it, it'll reboot, and there's another check going on there that if it doesn't in some way execute properly, it just reboots again and looks for the firmware again and downloads it and flashes it, and it kind of gets stuck in a loop there. So modifying the actual code as far as like executable code takes a little bit more work, but most of the stuff was straight up web pages anyway. You can put anything you want here. It's very easy. It's uncompressed, no encryption. Modify the entire web server however you want and then just flash it. That's really not fun though. So let's get rid of this thing. So taking a look at the very beginning of the firmware, this is the header. It has a structure to it, gotten the whole structure figured out, but the only thing that's important for this part is the start of it. It is a cold fire instruction to jump to offset 40,000 and 150 bytes in, which is where the actual code starts. So it jumps over the header. Let's change that to, jump to yourself. Try and create a little bit of a loop. And because we're using checksums, I don't even gotta know where the checksum is. It was 150, and then make it 00, and then take that 1 and put it 51, and then add 50 to the 54, and you get A4. I don't give a shit what those bytes are, because we're just gonna loop and jump to ourself anyway. So we've got a soft brick here. The device flashes itself. It gets stuck in this loop. Give me the firmware. Is it valid? Yes. Flash. Reboot. Oh shit. Is there any firmware out there at the same TFTP? You don't have to redo all that. It looks at the same IP address, same file name. Is there firmware there? Yes. Download it or TFTP transfer it. Flash. Reboot. Oh shit. Is there, So I let this go on for a while because maybe it'll break. It just keeps going. You can disconnect from the network, come back later, and it's still trying to get the firmware file from the TFTP server. So if there's a TFTP server at that IP address with the file name that it's looking for, it's going to pull it, and then it's going to just keep going. If you take the TFTP server down or block network traffic, then you can recover from the brick at that point. So let's go a little bit more ass kicking here. Let's break it. Tried some cool stuff called Elegant. Didn't really work, so I just kind of said. And I went into the what looked like a structure table. It looked like addresses. I don't really know what they were. I don't care what they were. Just move some bytes around. This is randomly picking bytes and then moving them somewhere else. Nothing more advanced than. So we get FPGA corrupt, and I was like, fuck yeah. And then I Googled it. So it's actually in the manual. When that happens, it will fix itself once. It doesn't say that in the manual. I don't know if there's anyone from Rockwell or Allen Bradley in here, talk to me later. I don't know if it was tested more than once. You tested it once and it worked, so it pushed out. I tested it twice and the exact same thing twice. And it was done forever. I said, oh shit. I need to confirm this, I need to validate it. Boss, buy me a new PLC, please. Okay. PLC gets in, 5 minutes later, bricked. So. The one on the kegerator, though, is still working just fine. As long as it's kicking. Everybody loves Shodan, right? And nobody puts PLCs on the internet. Except these 1,158 people that nobody has the current firmware version. Current firmware version is 21. Previous version before that was 16. Version before that, there was a series of 15s. The newest one out there are some 16s. There are a bunch of 15s. And they go all the way down to 1. And there's a couple 3s and some 4s, a whole bunch of 5s. I don't want to know what the hell these are hooked up to. Like, a lot of them are on wireless, like Verizon Wireless is the network they're on. I can just imagine they're out there somewhere out in the field with like a MiFi or something, and they have their own IP address. So somebody fix this. So we have a firm brick, but what about a hard brick? Say, I am not an engineer, I'm not an electrician, but I will tell you, do not fuck with electricity. The bad things happen. I'm not going to tell you what I did. It's pretty stupid, but I knew what I did as soon as I did it, because you heard the pop, and I smelled it, and I looked around. Does anybody see? Anybody hear? It's kind of, shit, it stinks. I tried to fix it. It's a fuse. I bought some more fuses, replaced it. I think I butchered it when I soldered it. It never came back. So I did not hack the hard brick. It was dumbassery that did it, but it's bricked. So that is, these are my PLCs, by the way. If anybody wants one. I actually fixed the hard brick by replacing the logic board in the one that I blew up with the logic board from, I took the good logic board out of the hard brick and put it in one of the firm bricks and got a working PLC out of it. So that was kind of interesting. But the other two are just, I don't know how to recover them. There's a serial port on it, and I've tried to hook up and see if there's any kind of serial console we can get to. Again, anybody from Rockwell or Allen Bradley out there want to help me fix these, I would be happy to share with the world how we fixed them. Also, I do need to point out, I had it on one of my slides back here. I'm not going to roll all the way back, but the newest version of firmware for the Micrologix PLCs may do cryptographic firmware signing. I say may because I haven't tested it. They have a new hardware version out there, Series C. I don't have a Series C PLC to test on, so I can't say that this, it doesn't work anymore. You can't push your own firmware out to it. I can't say that. Again, anybody from Rockwell or Allen Bradley, give me a Series C PLC and I'll be happy to test it out. And then let everybody know that, hey, I couldn't do this or I could. But I want to say thank you to Talos for paying for me to be here, letting me do this on the clock, and all the beer that was involved, because testing, when you're on a kegerator, you gotta, the whole point of the kegerator is beer, so every time we test, you have to validate that it still works, that it still pours beer. And then when it pours beer, it's like, is the beer still good? Because the beer can go bad. I also want to thank Moxa. They were really cooperative with sharing GPL source code, which can be a nightmare for some people. Finding an organization that actually responds to a request for GPL source code is rare. And they responded and they shared in a reasonable amount of time, so I got to give them a shout out for that. And to Rockwell for working with us on the coordinated disclosure. And anybody from Rockwell or Allen Bradley out there, come find me later. I want some more PLCs. Please. So I have enough time for questions. If anybody wants to shoot any questions up here, I'll be happy to answer them. If you don't want to ask them here, then I'll be here all weekend. So I can't see anybody out there. The bright lights are in my face. I don't know if there's microphones set up for questions or not. No? Okay. No microphones for questions? So thank you.